This video is part of a series about the computation and visualization of three-dimensional minimum spanning trees. In this video, I will talk about usage of the Boost Graph library. The Boost Graph library is actually pretty simple to use, but there were some things in the documentation that I found unclear. Hopefully this video will help. When you are wanting to use the Boost Graph library, there's three things that you need to think about. One is how to store your graph structure. I'll talk about that. Second, how to associate properties with your edges and vertices. Things like distances, weights, visited, things like that. And third, how to get those properties in and out of an algorithm. Things like shortest path, the minimum spanning tree algorithms, depth first search or breadth first search, and others. So let's get started with talking about graph structure. All of the examples that I'll be talking about in this video can be accessed on my GitHub. When representing a graph, you have two main choices. There are others, but these are really the ones that I consider. The one that's easiest to use is the adjacency list that comes with the Boost Graph library. You also have the option of wrapping an existing graph structure if you already have one in your code. And an example of this can be found in the CGAL library. Wrapping around an existing graph structure can be tricky, and there are some gotchas that you need to watch out for. And perhaps I'll do another video entirely about that. But for this video, I'll be focusing on the adjacency list. So here we have the documentation page for adjacency list. There's a couple of things on here that can be interesting to you. Adding a vertex. This is the global function. It is not a class method, it is a global function. So you will be calling, in order to learn how to use the adjacency list, it's probably easiest to just go to some code examples. Here is one of the files in my GitHub. So we start out with your normal includes. Here I've included a couple of web links that I think are useful in learning how to use adjacency lists and the Boost Graph library in general. Here are two structures that I will be using in this example for storing vertex properties. So vertex could have a name if you wanted. It could have a number if you wanted. Edge data can have the name of an edge, you can have a distance, or you can have anything else that you want to associate with the vertex or an edge. Here's the simplest example that I could come up of using an adjacency list. Adjacency list is a templated type. It takes a class on how you want to store your vertices and how you want to store your edges. Simplest I've found is to just use two vectors. Third template argument is directed, undirected. Here are your vertex properties. In this case, I am not associating any vertex properties. And third, and last, this is the type that will hold your edge properties. Also, in this case, we're not going to, in this example, I am not storing any edge properties either. Not a particularly useful example, but this is the bare bones minimum. And I include this in hopes that when you see this relative to the other examples, it will make sense. In order to build up the graph, you will call vertices, add vertex and add edge. Note that these are global functions. They are templated functions. So depending on the type of the graph that you are passing in, you will have the appropriate function called. So in this case, I'm adding two vertices and one edge. Once you have your graph built up, you can then iterate through it. We have a global function here, again templated, which returns a pair of the first and last iterator pointers. So that would be begin or end. And we see that how that is used here. We assign our iterator to the first of the pair and always compare to the second of the pair to determine that we're at the end of the loop. The same thing happens here when traversing the edges. Okay, let's go to something more interesting. Here we have an adjacency list where for the vertex data, we are using the class that we showed above. Let's go back there for one more time. Here's the vertex data. The vertex data in this case is the storage mechanism for the vertex properties. For edges here we're using the built-in edge weight property type, and definitions for each of the built-in property types can be found on the adjacency list documentation page. So here's the list, and here's edge weight that we're using in the example. When using this mechanism for defining properties, that tells the Boost Graph library, the adjacency list class, that I want to associate with this property tag here, I want to associate a double. That will happen for each of the edges. Now let's see how you actually access each of these properties. Here we create a graph with 5 vertices. To access a vertex property, you simply pass in the index of the vertex, followed by a dereferencing to the property. First name is defined in the vertex data class. And in this case, we are simply assigning it to the word Jeremy. In the case of edge, it's almost the same. Here we're going to add an edge. Now, the add edge function returns actually a pair. The first is a reference to the edge, and the second would be whether or not a new edge has been created. If you have asked for a adjacency list with no parallel edges, when you add an edge, it will not create a new edge if the edge already exists. And so it will return to you the one that was already there. And accessing the second part of the add edge return value will tell you whether or not that such a thing has happened. Okay? In this case, we're just adding the edge. We're not going to check the second. Here we have E. Now, how do we access the properties of the edges? Well, for that, we need to use a property map. Here we have a standard property map, which comes with the Boost Graph library. It takes the type of the graph, followed by the tag of the property that you're trying to find. Now, from this, it returns to you an object of the property map type. This property map object overloads the dereference operator. We then call the property map with the edge as an argument, and we can then assign the edge weight to be 10.1. 10.1 can be a float, because here we have put double. Once we've done that, we can then print out the settings that we just did. So here we say I want to access the 0th vertex of the graph and then get the first name out of it, which we assigned up here. An alternate way of accessing bundled properties, which that's what these are called. This is a bundled property. This would be a built-in, I call it a built-in property, though I believe that the Boost Graph library refers to this as an internal property. But a second way of accessing bundled properties, Boost Graph library has provided this helper function, get. Here you pass in a reference to where within this vertex data you will find the appropriate field. Pass in the graph that you are getting it from. So once you have that property map, this get will return a property map, which you can then dereference with the 0 index to get the same value. As before, when we assigned the weight map here, you can also extract the data out of there. Alternately, you can use this other get function. So a little bit of a diversion. There are two different kinds of get functions that you will find in the Boost Graph library. One of them will take parameters relative to the graph and return to you a property map. The other will take a property map, and instead of taking a graph reference, it will take an edge or vertex reference, and it will then return to you the value of that property. Okay, let's continue on to the next example. Here we have an example that is much like the one we just saw. Vertex data is still the same bundled property. For edges, in addition to the built-in property, we also have an edge data bundled property. You can combine the two. So as before here, we have a 5 vertex graph. We've assigned the first vertex to have the first name Jeremy. Now here's where it gets a little different. We've added the edge as before, but now we can call graph and dereference by the edge and then access the bundled property. You can still do it the old way. Oh, in addition to that, you can set the standard property, where here we get the property map for getting the edge weight, and then using the property map, we can assign the weight to be the same 10.1 as before. So again, note here that you can combine both the standard property maps as well as bundled property maps. Getting the name here is the same as before. For the edge name, again, we can dereference it with the same syntax that we use to assign the value. You can also use this get property map access function. Just like we did here with the vertex data bundled, you can also get the property map for getting the edge name. And again, note that here, this get, it gets a property map. Once you have that property map, you dereference it with these square brackets. Okay, two different kinds of get functions. One of them gets a property map, and the other type of get function will take a property map and a vertex or an edge, and the other get will return to you the value of that property for that vertex or edge. Moving on to the next example. Just like before, when we had a combination of standard properties with bundled properties, you can also have multiple standard properties. So here I am combining the vertex distance together with the vertex distance 2. Both of these are standard built-in property types that come with the adjacency list. Here I get the property maps for distance and distance 2, and here I use those property maps to assign values and then again to retrieve them. Okay, here I'm using the get function. You could also use the property map directly. Continuing on, this is a simple one where we have only bundled properties, vertex data, edge data. Otherwise, the example is very similar to what we've seen before. These are some of the things that you need to think about when creating your graph and associating properties with the vertices and edges. Now let's talk a little bit about how to use the algorithms. Here's one example of one of the algorithms that comes with the Boost Graph library. This is the Dijkstra shortest path algorithm. Now, I found that the documentation here can be a little confusing. Here we see there are 3 function prototypes. This one, then there's this one, and then there's this last one here. Personally, I don't use these 3, or here you can pass each of the arguments explicitly, but I found that the named parameters is an easier way to deal with it. Unfortunately, it's easy for this one here to get lost within these much larger templates once here. So I had a hard time really discovering and coming to appreciate the named parameters feature that the Boost Graph library has. So I will be focusing on just this first prototype. So Dijkstra shortest path takes a graph of your type. It can be your adjacency list or it could be your wrapped graph type. It takes a vertex descriptor, which that is the shortest path from where, right? This is not a all pairs shortest path algorithm. This is, I have this starting point here, and I want to know the shortest paths from it to each of the other vertices in the graph. And then last is a single parameter that is a combined named parameter list. And we'll see that here in just a second. So here is my code example file for showing how to use the Dijkstra shortest path function. Again, it can be found in my GitHub. So as before, vertex data bundled prototype. We also have edge data. So there are a couple ones here that I've added relative to the previous examples. One of them is a predecessor map property distance. One of the things that you can compute is how far you are in each of those shortest path computations. And then here I have for the edge data, I have a distance of that edge. Here we have first example, adjacency list, no vertex properties, single property on the edges for storing the edge weight or the distance of each edge. I create a simple graph. Here's something new. This add edge, we pass in something of type that matches the edge property. You can also do the same thing with add vertex. So one way that is demonstrated in the documentation for passing properties to algorithm is using an iterator property map. Iterator property map at first I found to be a bit confusing, but it's actually pretty simple. It is a property map. It is a mapping from some sort of an iterator, be it a standard template library iterator. So if you have a vector, you get an iterator from it. Or alternately, you can also use a straight C array, and then a pointer is also viewed as an iterator within the standard template library as well as here in the BoostGraph library. So first off, it needs to know the type of your iterator. In this case, we're using the iterator of a vector of the vertex descriptor. Additionally, I have here this ID map property. There are some graphs where the graph itself is not indexed by integers. In the case of adjacency list, it is, but it doesn't have to be. Because the BoostGraph library tries to be generic, it will also ask for an ID map. The adjacency list comes by default with an ID map to go from a vertex descriptor into an integer, and that can be accessed here. It's one of the standard built-in property types. So this is a simple type that we're passing into this iterator property map. And then the last two are simply a vertex descriptor class, because again, this is a typedef, as well as a reference to the vertex descriptor class. So this could look confusing. This line here can look confusing, but it's really not. And in a lot of ways, you kind of just cut and paste it and go on about your day. Now that we have the iterator property map type, we will instantiate it into predmap. And into that, we pass a pointer to the beginning of the list. This list is assumed to already be allocated with the number of entries needed for either the vertices or for the edges. And we see that up here, that when we created the predecessor list, we passed in the number of vertices that we want. And then as the second argument here, we simply get the property map to get from the vertex descriptor into an index into this guy here. So that's an example for using the standard template library vector. But you can also just use a C array. So in this case here, creating a C style array pointer, mallocing the number of vertices entries into that thing. Here I again create the iterator property map. Instead of taking a vector iterator, I simply take an int star, because again, the standard template library and Boost look at pointers and container iterators as being the same. You can do all the same operations on it. You can dereference them with the star operator. You can increment into them using the plus or adding numbers to it. In those ways, a vector iterator and a pointer, an array pointer, behave the same. Again, we want the same vertex ID map, and in this case, the type of the map is integer and integer reference. Which one thing that I did not mention up here before is that because this is the predecessor property map, we want to know for each vertex what is its predecessor vertex within the shortest path. Right? So in that case, we're not returning a distance. We're saying this other guy is the one that's before me when in the shortest path. So that's why we have a vertex descriptor here, and that's why we have an integer here, right? Because in this case, we're saying the vertex is this far from the starting point. And that distance, in this case, we want to represent as an integer. Here we instantiate this property map that we just typed with the array. And here we're actually passing in a array pointer along with the vertex index as before. This property map is the same as the one that we just did with malloc, but instead we're using a vector. And so here we will see in the two calls to Dijkstra shortest path how it doesn't really matter whether or not you are using vectors or C arrays or some other structure. So They both take the graph pointer. They both take a descriptor to the vertex that you want to use as your starting point. And here is kind of where the magic begins. Here we are doing the named parameter. Note here that this is a period. It is not a comma, right? So these are not two separate arguments to this function. These two together constitute one argument. And then the Boost Graph library knows how to extract out of those the arguments that it wants. So here we are passing the predecessor map property with this mapping function. And again, here we are not passing in an array for where the property should be stored. We are passing a mapping. And that's very important because there's a lot of places in the algorithms where these things are passed around by value. So you really don't want these things to store any real data because all of that data will be copied each time that pass by value happens. How did I know that predecessor map and distance map are the ones that we wanted? So let's go to the documentation for that. Here we are back on the Dijkstra shortest path documentation page. If we scroll down, we will see the parameters followed by named parameters. These are all the parameters that can be passed into this particular algorithm. A weight map for knowing the distances, index map, which we've already talked about a couple times. Predecessor map is a return value. Then we have the distance map, distance compare. In each case, these are the strings that we care about. In our case, we have predecessor map and we have distance map. These two are the strings that are then used here within the named parameters. You take the name of the parameter, and then to that you pass the mapping, name of the parameter, and we pass a mapping. In this case, we're passing a mapping that takes a vector. In this case, we're taking a mapping that takes the integer pointer. Also note that the order does not matter. Here we have predecessor map followed by distance map followed by predecessor map. Let's continue on. Here we have another adjacency list using the bundled properties feature that it provides. Vertex data and edge data. In this case, when adding edges, note that I am passing in a static value list. Edge data has two members. It has edge name and it has distance. You can initialize edge data like this. Add edge as the third argument simply takes a value that matches the type of the edge property. And so that's why this works here. Alternately, you can use the same syntax that I showed you in the adjacency list examples. In that case, as before, as I showed in the adjacency list examples, you can get a property map by passing in the location of the property into the get function here. This will return a property map, and then you assign the named parameter with that property map. So here we are doing that for the predecessor map, distance map, and weight map. Note here that we are combining vertex properties with edge properties. Moving along, you don't have to use the built-in property maps that the Boost Graph library provides. You could also implement your own. So for that, you want a class that has these type defs within it. The value type is the type of the property. In this case, it's int. You have a key into the map. Is it an edge descriptor or is it a vertex descriptor? Here, you construct your map in whatever way that you need. And again, note here that it is important that you are not storing the actual mapping data. You are storing a reference to it. These objects will be copied by value many times. So in this case, if I were to just use a map here without having it be a reference to a map, that map would be copied many, many times and your algorithm would slow down immensely. So here I have a class which has a getWeight method that the adjacency list that the Boost Graph library doesn't actually access directly. The way that it gets to your property values is that you also have to provide a global function called get, which takes the property map object, takes a key into that mapping, and then it will know how to return a value. So in this case, it takes the weight map that you're passing in, you're calling this method name and giving it the key to your edge in this case. This getWeight and this getWeight can be whatever you want it to be. The only thing that you really need to worry about is that, again, all of this is copied by value. And if you are passing around a lot of data, then things will slow down. I was bitten by this once and it took me quite a while to figure out why. Kind of why I'm harping on it here. Distmap. It's another implementation of a property map for the distance. In this case, we're using a vertex descriptor as the key, but otherwise it's basically the same integer. In this case, I provide a square bracket dereferencer, which I can then use here in this global get function to return the distance map. Additionally, because the algorithm wants to actually set a value for the distance map, you also need to have a put function. Put function takes the property map, the key, as well as the value that it wants assigned. And here we will call the dereference operator with the key, and here we will assign the value. So this is a bit more complex than just using the built-in BoostGraph library stuff, but in some cases, you need to have this control. This is particularly true if you're wrapping an existing graph data structure, and that graph data structure has its own storage within it. You can then use these mappings to assign values into the graph directly from the BoostGraph library algorithms. And again, remember, these are mappings. These are not containers. A last example here. We have this mapping that we created. We have a dereference operator, which returns a reference to the value, followed by this get and put functions. And these things are pretty simple, and it turns out they're actually pretty standard as well. You take the mapping, you call dereference with the square brackets on the key, and you either get or assign the values. BoostGraph library has a way to simplify this so that you don't have to implement these get and put functions yourself. So here's an example of that. Here we have a predecessor map class. It derives from this put get helper, and with it, everything is the same. Everything here is the same. This here is the same. But because you are providing a dereference operator or a square bracket operator that returns a reference to the value type, it can then create the put and get function for you. So let's see how all of these things are being used. To create a simple graph, we have a map from vertex descriptor to vertex descriptor. In this case, this is a container, right? So here we have to be careful to not confuse our terminology. Here we have a STL map, and here we have a property map that takes that STL map and enables the Dijkstra shortest path algorithm to then assign predecessors. So we're taking this my pred map, and passing it here into the pred map. Similarly here we have a vector. This is the actual container. This dismap is a property map on that container. Here we have dismap. So we're taking that property mapping and passing it into this dismap here. And my weight map gets passed into the weight map here. So in this video, I've covered several things that I have found were tricky to learn from the documentation. I started with talking a little bit about the graph structure, the different ways that you can use adjacency list, either by using built-in properties or by using bundled properties. Then talked about how to access those through property maps, either by using the get function or by dereferencing the graph using the square bracket. And then last, I've talked a bit about how to use the algorithms and the different ways that you can pass in the properties. So it's taken me a little bit to get through all of this, but my hope is that by seeing the differences between the different ways of doing it will then make it easier to know how to proceed. The examples on the documentation only have single examples, and in my experience, it was really the deltas that finally helped me understand that the BoostGraph library is actually pretty simple to use. I hope this was helpful for you. Please comment, and happy graphing.